Right.
Okay, does that make sense?
Sure.
So
It
the one
does.
from so what we're looking for is the shape of the function, and
Mm.
that's what we're gonna get as we go down. All right. I hope it makes sense, just me explaining. Madam Taban
Now
can
that
look at draw function.
it makes sense.
All right. Okay, so let's go back to drawing this function. Some of these properties we'll use later on, and so that they can make more sense. All right, so the first thing first, we'll take that function, label up a sketch. So they want us to sketch the function, which is f of x is equal to that, x to the power 3 minus 4x squared plus 4x. The constant is 0. So if the constant is 0, the graph will cut the y-axis as 0. So we already know. All right.
Right.
Now show all the stationary points. By stationary points, they mean the turning points, the local minimum,
Right.
local maximum, the intercept
Right.
with the axis, and the point of inflection. All right. So we'll start with the stationary points. Usually I like starting with the stationary points and then go to the intercepts. By starting with the stationary points, it's easy for me. All right. So we'll start with the stationary point, which is the local minimum, which is the local minimum and maximum turning point, okay? Which are TPs. Now at the turning point, you have f prime of f of x. I'm just gonna write the function again. That's f of x equals x to the power 3 minus 4x squared plus 4x. So at the local minimum and maximum turning point, we're actually looking for f prime of x. We're looking to differentiate this function, because that's how we find a gradient. So we're looking for a gradient of a function. Remember, a gradient of a function will be found at f of x is equal to some value m. So let's say the input value will be f of a. For example, the output will be some value m. The a will represent some input value. But this is what we're looking to find the gradient, all right?
Yeah.
So you could use the notation f prime of x if you do want, or you could use the y over the x, or you could use the f of x over dx. All right. Basically, what you're saying is that you differentiate. Remember, look at there is the limit notation.
Yeah.
Is 0. In a f of x plus h minus f of x all over h. What we're saying is that the limit as the f approaches 0, we're finding this is the rate of change, which is this topic is about, the rate of change of y with respect to x, the rate at which y changes with respect to x. With respect to x, which simply means basically a slope or your gradient. So we could say this is your slope or your gradient. So this whole thing comes from, these are just basically notations, different notations. I think this is Leibniz notation, or this is Newton's notations. I don't remember clearly, I'm not really interested. But they're different notations that mean the same thing. So we're going to differentiate this function using the power rule. The power rule says if we have a function y, or the function f of x, equals x to the nth power, okay? What we'll do to find the differentiation of this function, which is f prime of x, we'll then take the exponent n and multiply the coefficient. This is called the function. The x is called the function. And multiply the function x, right, with the exponent n. So I'm just gonna, and multiply the function, or rather the coefficient of the function, in this case it's a 1, and multiply it with n, which is the exponent, and from that n again we subtract a 1, and that's it. So this right here is what we're going to do. All right. I may be over giving information here, but such as you can understand. So I'm going to take that function, which is basically is the quadratic function. Also, look at that is three separate functions, 1, 2, and 3. So this is the cubic function, quadratic function, and a linear function. All right. So look in the university, but treat that as individual functions. But right now, we're just going to think of them as just like one function. What are we going to do? I lost him. I think I lost him for a moment. I think he will be back. Okay, I think I got you back on. Where was I?
Right, you were explaining the rate of change. That was my fault. My PC just turned off. Right, I'm back. Sure.
Okay, so this part right here, did you get this part right here, saying this is the rule that we're gonna use?
No. I missed that. I missed that part.
Let me just explain it. I was saying if we have a
Right.
function y is equal to f of x, which basically x to the exponent of n, all right? That will be our function.
Right.
To get the derivative of the function, which is f prime of x, I'm going to use one notation. Well, you could use the dy dx, df of x over dx.
Oh, okay. Sure. Now I get it.
We take the exponent of a function. The x is referred to as a function. So what we do, we take the exponent of a function, multiply the coefficient of a function, all right? And then after subtract the 1 from there.
Right.
Okay, this is called differentiation, or finding the derivative. Let's just call these differentiation. As a matter of fact, this is differential calculus, by the way.
Right.
All right, so what we're going to do, you will treat each and every term as a function. So what we'll do, we'll say that this is a cubic function. For example, this is a cubic function. This is a quadratic function. This is a linear function. And this is a constant. Also a constant is a function. Did you get what I'm saying?
Yeah, I get it.
All right, so in every function, take the exponent of the function, multiply the coefficient of the function, subtract 1. This is a quadratic function, you take its exponent, multiply the coefficient, subtract 1. This is a linear function, you take its exponent, multiply the coefficient, subtract 1. However, the derivative of a constant, since this does not have the x, does not have a function in itself, the derivative of a constant will always equal 0. We cannot differentiate that thing. All right?
Right.
Okay.
So
what we do, we go back to this graph. Okay. We'll take the 3, we'll multiply the 1, and then there's going to be 3x, and then we'll subtract the 1 from the 3, that's going to be 2. So 3x squared minus 2 times 4, that's going to be 8x, and then The derivative of a linear, however, like I said, the derivative of a constant is 0. What do you think will be the derivative of a linear function?
It would be 4.
Very good. It will be the coefficient of the linear function. Simple as that.
Right.
All right. So here we have our derivative. All right. Now again, remember for stationary point, we just have to tell them this. Every time you can say dy dx, dy over dx, or if you want the f prime of x equals 0 for your local minimum or maximum turning point. You get what I'm saying? So whenever we get local minimum or maximum turning point, our dy dx is going to equal 0. Does that make sense?
Yeah, it makes sense.
All right. So we're going to take that gradient linear and which is was it 3x squared minus 8x plus 4.
3x.
3x squared minus 8x plus 4, and then I'm going to equate to 0. This is a quadratic. I think this is where you come in at some point. Now that we've created a quadratic to 0, we need the roots of this quadratic. Every time we equate to something, this is a function as well, all right? And I'm just going to highlight for you that you have to know that this is a function. But it's a quadratic. Like a function, ilava the roots tayo. So the roots tayo, that are basically a turning point of their functions. If you think of it, I just want you to think of it like that. The roots
I get it.
The roots of this are going to be the turning point of the other function.
I get it. Right. Since these,
we're just gonna do this 3 by 2 is gonna be a 6, and a 2 is gonna be an 8. I think it will work that way. So I'm gonna factorize this. It's gonna give me a 0. It's gonna be 3x and x, and then I'm gonna multiply the 3 by 2 to get a 6, and then I'm gonna subtract a 2 to get an I'm gonna add a 2 to get an 8. So I'm gonna put a minus because the milli term is a minus here, if you say that. Okay, so both factors should be minus. Negative 2 by negative 2 should give me a negative 4, and then I'm fine. So I'm gonna have 3x equals 2 or x equals 2. So your x is gonna equals 2 over 3, or x is going to equals 2. Now these numbers are my x values of the turning points, if you get what I mean. All right.
Yeah, I get you.
Not the y values. So you could just right away substitute it into the function, back into the function, to get the
y values.
So I'm going to look for f of 2 over 3. Remember the function is this
x cubed minus x squared plus 4x, right?
The power 3 minus 4 into 2 over 3 all squared. What's next? Plus 4 into 2 over 3. All right, into 2 over 3, and then I'm going to get output value, and then I'm going to have f of 2 as well, which is going to be 2 to the power 3 minus 4 into 2 squared plus 4 into 2 over 3. Now we're just going to punch a calculator to see what the output values are. Just to be fair and square, I'm trying to pull out my calculator. Now with the work on
right.
plus 4 divided by 3. Oh, I forgot to square the quadratic sign. I get this 1.18. I wanna try to find the fraction of that's 32 over 27.
Right.
Uh,
I also found the same thing.
okay, 32 over 27. 32 over 27. Okay, so lay one kabeman.
The X
turning point. Yeah, 2 over 3. We don't know whether it's a minimum or maximum turning point. And 32
right.
over 27. 32 over 27 is something equivalent to 1.185. Leave it like that. And then la, it have 2. And what's the output value here?
I got 0.
You got a 0.
Right.
All right. So you got a 0. Now also that tells us something. So another turning point, and then we got a 0. Now, so in that turning point in Berry, this one right here, and then this one that right here. But we don't know which one is the minimum and which one is the maximum turning point. Okay. So
right.
to determine which one is the minimum or which one is the maximum turning point, we can do a second derivative test. All right.
Okay.
Now you do this to test which one is the minimum and which one is the maximum turning point. And second derivative also is that there is to get our point of inflection, and we're gonna come back to this later. Or we can just immediately do that after finishing our stationary points, because I don't want to go back again. So now what you're trying to do, you find the derivative of a derivative. It's very hard to just pick by eyeballing them, which one's going to be a minimum, but I already see which one, because they can automatically come out when you create a graph. But you don't want to do that, you just want to test them. So the second derivative will be the squared y over the x squared, meaning what you're trying to find is f prime of x. So you take the differentiated function, which is the quadratic, right? And then so you're gonna differentiate it into obviously a linear. So your cubic will differentiate into a quadratic, your quadratic will differentiate into a linear. So we want this part. Okay, so I'm gonna take this part and differentiate it. Let me just put it right here. So what you want to do, you want to find the derivative of this derivative, again using the power rule. Okay, what will be the differentiation of this using the same method?
Let me just, it will be 6x minus 8.
Minus 8. Can you see my linear function?
Right.
This is a gradient, and then this is a constant in a sense. Okay, so kind of makes sense that way. I'm just highlighting some important things that you will need to watch out in the future, right?
Sure.
I want you to kind of develop the eye for that. So, all right, now we don't equate this to 0. We only do that with our point of inflection, of which we're going to do that in a second. But this time, we want to test whether we get a positive number or a negative number. Look, we input this value right here or this value right there. You get what I'm saying? So
yeah,
look, we a negative number. Okay, we're gonna interpret that to mean that we get a number less than 0, and the number less than 0 will mean for us a maximum turning point. Remember, when an a is equals to 0, right? Sorry, when an a is less than 0, we get a maximum turning point on our quadratic. So what we actually did was to differentiate our quadratic to get its turning point based on the input value input. All right, we could input a 2 over 3 and a 2, which is important. So we're going to input first 2 over 3, which is the one that we got here, and let's see that again. So we're going to have 6. Then I'm going to input 2/3, all right, close bracket, and then minus an 8. I just want to see if I get a negative number or a positive number. Now, this is going to be a smaller number compared to 8. And if I'm subtracting 8, I'm going to get a negative number. I'm not interested in the answer. Now, since 2/3 gives me a negative number, all right, I'm going to associate the turning point that is associated with 2/3 input value x, all right, with the maximum turning point. So this turning point here is going to be a max TP. Now, the other one, which is going to be 6, this time I'm going to input, remember, is a 6x minus 8. This time I'm going to input the value 2. It's going to give me a 12. And if I subtract 8, it's going to give me a positive number. That's all I'm looking for. If I'm getting a positive number, I'm going to interpret that to mean a minimum turning point.
So if it's a negative number, it's a positive turning point, and if it's like a positive number, it's a minimum turning point.
Exactly. So in terms of a parabola, right? Because the turning point led to combat the parabola that way.
Oh yeah. Sure.
You have a minimum turning point. If you have a positive, you have maximum turning point. I kind of like tell people to think of it like that. But yeah, it also gives us some more information into that, which I'm gonna tell you about later on. But just as something that helps people remember, I always do that. All right.
I get it.
So I did the turning point there again. So number 2, I'm gonna try to find a point of inflection because they looked at that, right? So I'm done with finding the turning point. So the point of inflection. As cool because I'm just teaching, so I'm touching on more things. So the point of inflection is found at the squared y over the x squared, which is also f prime of x equals 0, right? So we're gonna equate the second derivative to 0, and we know the derivative, which is 6x minus 8, we equate it to 0, and then 6x is 8, and then x is 8 over 6. 8 and 6 are divisible by 2. Here the remainder is 4, and here the remainder is 3. So x is going to be 3 over 4. And then we'll go back to the function. We're looking for f of 3 over 4. So we're looking for f of 3 over 4 for an output. Don't be like calculator and then I'm going to go to the command. Remember, you substitute this into the function. You're going to go f of, and these notations are important. That's why I'm insisting on using them, because sometimes when we get a question about f of 3 over 4 is equal to some output value, what does that mean? All right.
Right.
Not 3 over 4, 4 over 3, excuse me.
Second derivative is equals to 0.
0.
Did you mention why?
I want you to input this value right here back to the original function and see what the output value.
Okay. Let me do it now. Over 3 minus 2 plus 4 over 3 without the calculator. Right. Yeah. I put it back into the calculator.
Yeah.
And I got 16/27.
16/27.
Right.
16/27 is a value equivalent to what at most? I think
Something like 0.6.
0.6. So between 1 and 0.
Between 1 and 0, yeah.
Right. What about 4/3?
4/3.
1 and something.
4/3 is what is 4? Nah. 4/3. 3. Yeah, it's 1,3. 1,3.
1,3 something. Okay, so we have those values just so we can know where they are in a graph. Okay, so we're done with this part, and this is a point of inflection, by the way.
That point is the point of inflection.
Okay, no point of inflections, by the way, right?
Sure.
Kind of sort of divide the positions of the concave down.
Right.
All right. And the blah blah saw later on. Yeah. All right. Now we need to go into the intercept. So this will be number 3. So we'll start. Usually I start with the y-intercept because they're easy to do. I'm just looking for a constant. Y is equal to some constant d. Now, do we have the constant there now? No, we don't. So the constant is going to be 0. So the y-intercept will be at 0, and f of 0, we'll see what f of if y is, if x is 0, because obviously like letter x was 0. So we're going to intercept the 0 and 0. All right. And then we get, let's just call this a, and then b, we'll get the x-intercepts. All right. Other than for this function, remember the function is x to the power 3 minus 4x squared plus, is it plus 4x?
Yes, plus 4x.
All right, like over 3 times is easy and straightforward, but usually we're not the method related to the cycle. I remember taking you through number 1, synthetic method,
and the
for finding the roots.
NSC.
Done this, and the other one was the inspection method.
Yeah, the inflection and the synthetic.
Okay. So usually we use these two methods, but I don't think this function will need that. I think it isolate x, we can take out the factor of x, and then the sine x squared minus 4x, and then plus 4 equals 0. So one factor of x is 0, and then we just have to factorize the x squared minus 4x plus 4. Let me just do this before ni equate the 0. So we could factorize this. I think minus 2 will do. Will minus 2 do? X minus 2 and x minus 2. Am I wrong?
Let me. Nah, that checks out.
Yeah, look, I'm gonna show we could use the quadratic butterfly, right? Because this factor came out, and then so I'm gonna equate x to 0, x to 2, and x to 2. Now this root is coming out twice, okay? And I know that how, because I want to scroll back a little bit and watch this and show you something, all right? Because I now will come back to graph as well. When we go back, one of the input value like turning point was a 2. I wanted to highlight that. Was a 2 and 0, okay? Now, this means f of 2 la equals 0. Once f of 2 equals 0, right? We have to know f of x is 0. look at f of x is here ngana 0. What we're looking for, because look at f of x is ngana 0, it's the same thing. Look, ulaba y-intercept, ulaba x-intercept, let y equals 0, because f of x will represent a y, okay? So if you let y equals 0, whenever y equals to 0, what you're gonna get is more of a root in a sense, okay?
Yeah.
All right. So look why you were ngana 0. Lesho ngata shikuma, right? It's an x-intercept.
Intercept, right?
Exactly. So now like the f of 2, f of 2 you money 0. So look, whatever input value laying I kumala, then that value becomes the root. In this case, the root is going to be a 2. So that 2, f of 2 yinika 0. So let's agree, logo letter y was 0, x money e 2. So no surprise that number comes out as then. So most of the time, logo turning point, look the output value of that turning point of that input value gives you the output value as 0. That number is going to act number 1 as a root and a turning point, meaning that when you go to finding your roots here, that number should come out how many times?
That number should come out twice.
Twice. Does it make sense? We could have the other one.
That makes sense.
I don't care, but that number should always come out twice.
Sure.
All right. So, but I'm gonna will say this is just me showing you how to navigate this. The questions, however, are a little bit smart and witty in an exam type of questions. But this is showing you here, right? That's where they catch these kids. Because a lot of learners are just interested in, oh, let me just plug in, how do we do this? And not looking at what's really actually going on. And they just throw this thing right here. This thing right here. And if they do this, right? I'm going to tell the kid, look, f of 2 is equals to f of 3, which is equals to f of 1, which is equals to 0. They are talking to you there, all right? What exactly is it that they're saying? If you would help me through this one.
They're saying that if you wait in the function, if you substitute x with 2, 3, and 1, y will be equal to 0.
And then what would this number then mean? I get that. What would these numbers mean? 2, 3, and 1.
It would mean that that the x values for the roots would be, I think, would be -2, -3. X I had like I think it would be x minus
yeah, those x minus 2, which x is equals to 2, and x minus 3, which is x to 3, and x minus 1, which is x plus 1. These would mean that our roots are at these points right here. These points will represent our roots.
Roots, sure.
But now, so if logo fakuma function yellow, very easy given these numbers. You kind of get what I'm saying. So these numbers will mean our roots. But they'll also do some other things else. Like a differentiation. All right. What would this mean? F prime, for example, of, let me just again use 2 is equals to 0, because they use a 2 there. Let me just fix this part and that's 0 according to the function, so it will make more sense. So la, in interpretation, we could say we're at f of 0 is equals to f of 2, which is also equals f of 2, which equals 0. All right, we know what this means. These are roots, and we have a repeating root, and no wonder this also comes out. But this time around, we have f prime. We have f prime of 2 equals 0. What does this mean?
Yeah, you're talking about the derivative.
Yes. Okay. What does this mean? What does this mean? As we've already said, f prime of x equals m. All right. What does this mean?
it means that, okay, sure. It obviously means that the derivative is equals to 0.
Okay.
Um,
But M
Meaning
here
that
is
the
followed
gradient
by
is also
okay. The gradient is equals to
right.
0. But
0. Right,
then
right,
what
right.
does this
So
number
I'm
then
thinking
tell
about
us?
this number tells us that uh the wait, hold on. It's literally right here. I wanna be able to articulate it correctly. I know that when you it means that I'm thinking right now what's in my head is I'm thinking about the straight line that intersects the turning points
Very good.
of the minimum and the maximum so the maximum turning points of the graph. So now in my head I know that y is a constant number. So
Mhm.
when that is 2, let me
Mhm.
check. When that is 2, it means that the y value of either one of those uh gradients. So yeah, either one of those like lines, those
Mhm.
straight lines is equals to 2. I think I'm not quite 100% confident, but
X.
either one of those two.
Remember, at the turning point, you know the value x and y. Okay,
Right.
at the value x and y. And turning point, yeah, you make a differentiation with respect
Sure.
to x is equals to some slope. All right. Now, the 0 is the slope that we're looking for. And once we see this slope, right? Now, the slope shall function is Tamash change, but we're interested in the slope shall function at 0. Now, we know good logos slope or gradient the function is at 0, it's like a turning point. All right? But a turning point like you come some input value x. Do you get what I'm saying?
Right.
So logo input a value to specifically you go with the slope shamani. You go
Sure.
at 0. Right, Malogo and Gigi, we got some other number, we'll get some other gradient other than that. But when we put this 2, and the other one was, I think was, what was it? 2 over 3. Only when we put 2 and 2 over 3, we get the output what? 0. Meaning we go gradient, yeah. And logo input a prime. You go gradient, yeah, money. Yeah, 0. Logo input a 2. So the 2 becomes the x value of the turning point. Now, this does not
Right.
give us the y value, however, of the turning point. It gives us the gradient.
Oh, sure.
We'll have the y value of the turning point. We'd have to take this 2 and input it back to the function, not to the f prime. The f prime is not the original function; it's the differentiated function.
Repeat that as well for me, please.
Okay, the f prime of x is not a function; it's a differentiated function.
Is it right.
So the work f prime of x, you can get m and now f prime of 2, right? You can get this does not represent the output value. It represents the gradient. Okay. However, here the 0 here represents the output value. Do you get what I'm saying?
Yeah.
Here that does not represent the output value, so you have to be extra careful. But is this how to like what input the f of 2 into the gradient?
F2, right.
No, we don't get the
No,
output
sure.
0. We get the gradient 0, making this the x value or the x coordinate of the turning point. If we want the y coordinate of the turning point, it's not going to be this one. All right, we have to take this number, put it to the original function, and get the y value of the turning point. It's just that it's a coincidence that this time around also we got it at 2. All right, but it's not
Right.
right.
Sure.
Okay, now I'm making you smart because these are the things that you should be looking for, and in the way that I'm showing you. All right, so we're not just doing this blindly. So we kind of painted some context into that. I hope you forget that. But also, I'm recording this meeting. I want to make sure that I send you that you can also be able to go back through this, even while you're doing
You
all
know,
problems. You would understand what we mean. So
appreciate that.
turning point in quad in the x values, not the y values. I think we're ready to sketch the function. So remember our function shape here called it a minimum turning point, it have a maximum turning point, minimum turning point. So it's gonna go more like this. You get all right, cause of the fact that our a is a positive. That they call that an increasing function. So I'm gonna just go ahead and sketch it here. And again, we're just gonna squeeze everything within a very small space. Okay, so my roots are 2 and 2. That root's gonna be 2 for the turning point. The other root is 0. Remember, I'm going to y-intercept it. All right. So I'm also gonna need my origin, and the turning points that made the thing on E2, and I'm gonna use a pencil. E2, ne, and some number. I think it's a 2 and some number 0. Remember, the 2 and some number 0 was a. If we go back there, we'll see what turning point was. Okay, 2 and some number 0 was a minimum turning point. So I'm gonna draw this more like that and just make it as a concave up so that you can see what's happening, right? And we're at another turning point. The other turning point was 2/3. Let's see the equivalence of 2/3. What's 2/3 equal to? I think 1 and 7.
What's 3/3 over or is it 3/2?
2/3. It's 1 point something.
Let me see. Yeah, it was no. Wait, sorry, let me fix it.
It's 0.6.
Over 2.
Between 0 and 1.
The 2 is over the 3, right? It's 0.6.
Okay.
So,
let me just delete this first so that it will make it. So naku stretch nyana la kuri ita kota ku enta nyana so ku make nyana sense. I'm just gonna put the 2 here and then put that point, and then the other one is 1 point something because I want to put a 1 there. So that turning point there between 0 and something like 0.6. That will be this number right here. And the other number, which was the output, was let me just scroll back too fast. Was 1.18 for the y, somewhere around there. I'm gonna just make sure the point stays here. So I have this point and that point, and then I'm just gonna go down that direction. So that's gonna be a maximum turning point. The other one is a minimum turning point. Let me just stretch it a little bit to be generous with the Kotakuska check. All right.
Sure. 16.
Kotakuska check. All right. So I'm gonna have this one right here, like that, and then this one right here, like that. All right. I think it does the trick. That's a marker 0, remember? And then I'm going to push it up just like that. So that's how my graph is going to look like. This is a turning point at 2 and 0.
6.
At 2 and 0. Let me just write where it is. 2 and 0. And here is the maximum turning point at 2/3. And I think it was 27 over, which is 1,1 something. It was 32 over 27.
32 over 27.
32 over 27. And then what else do I have? I also have my root. Obviously this root is 0 and 0. And the other root was 2 and 2, and then 2 and 2 as well. 2 and 0 and 2 and 0 as well. So this will act as a root and then as a turning point. So it makes sense. It touches there and then go back up, just like that. So that's our function.
3.
It's going to look like a point of inflection is between here and here. I think it was something like where was 4/3, which is 1.3, and then 16/25, which is 0.6. So the y was 0.6, so it's somewhere here. Y has to be below 1, 0.6, and then 1 point something. So I think that would be fair to say that's where my point of inflection is.
Right.
All right. Let me just
and then,
just so I can indicate it, because I gave it a so
yeah.
4/3, 16/27. I prefer writing
yeah,
16/27.
I do 27. It's
All right.
like 5 something.
All right. Does that make sense?
Yeah. Yep.
So that's all that goes into there. We're going to try another one and see if you got your footings. But this time around, you'll be doing most of the work. All right.
Sure.
Okay. So, la. I don't want to overly annotate this. La ina some point, but I'm gonna show. Let me just wait, because we're gonna get into the interpretation of the function. It will make more sense. Right now, I just want you to be acquainted with basically sketching the function. Let's take another question. I think we can take this one. Again, you could go to this example. The textbook, you get more questions on sketching. That will be fine. All right, like I said, you will be doing most of the work when it comes here to this part. So let's just go ahead and point some few things before you begin. All right. So first we have our function, which is negative x to the power 3. What does that say to us?
Let me just write it down. Sketch the right. The question was x equals negative x squared q plus 7x 2 minus 15x plus 9, right?
All right. What does the fact that we have a negative x in front mean for us?
That the concave, it's concave concave down is first, or at least the minimum telling point is the one that goes first, and then the maximum, like yeah, like that. Like I'm sure you have the picture in your head.
Right, I get it. Okay, so I think we can go ahead and sketch it. Let's just find the stationary points first. After finding the stationary points, you tell me you're done, and then I'm gonna also try to find the stationary points as well, and just so we can see if they line up.
Stationary points. Is that me? Oh, I deleted. Ooh, right. I sent it to him. Oh, no. Dude, I usually want it. Every day, me. My heart's got chance missing. My heart pumping is in it to keep rolling. Numb to it. unless you want to bring a gun to it. Double tap. How do you 14 next moment? That's a 3 Yeah, who knows, man? 0. It is 5 and 3. Like 5 and 3. Um, 3, 5 and 3 equals 0. Is it though, my friend? Is it right? It is. And down to it. The one that's in is always on top. Right. It is always on top. It is always on top. Right. That means that we move double time unless you want to bring the gun to it. Should I give you a warning? My heart's got chunks missing. My heart pump venom in a tub. Keep rolling. Keep rolling. Numb to it. Unless you want to bring a gun to it. Double tap. And then you try to run to it. Yo. That 3, 5, 3. It's the same digits all over again. I mean, it's pretty much the same, I would say. Negative? Negative 3, 2, 2, 7. Is 3, 0. Right. I found the stationary points.
Okay, go man.
What are you looking for? The coordinates are just like the oh, you're looking for the coordinates. Right. I found 5 over okay. One coordinate is 5 over 3. With the x being 5 over 3, and then the y is negative 32 over 27. And then the other coordinate, stationary point, is 3 being the x coordinate and 0 being the y coordinate.
Okay, what does 3 and 0 being 3 and 0? What does it tell you about 3?
What does that tell me about 3? It tells me that 3 is tells me that what does it tell me? It tells me that 3 is not a what?
It's also your root. That's what it tells you.
It's also a root, right?
Yes.
I was sort of unsure as to put there.
Oh, yeah. Sure. Okay. All right. Let's just see and just confirm. So I'm gonna be looking for f prime of x, which is negative 3x squared, and then plus 14x is 1, and then minus is it 15? All right.
15 x. No, just 15.
That's 15. All right. So f prime of x is going to be 0 for local minimum and maximum turning point. It's almost.
Agreed.
And maximum TP. So we're going to take negative 3x squared plus 14x minus 15 to be equals to 0. All right. What I would like to do would be to, obviously these terms are not divisible by 3. Only 15 is divisible by 3, not 14. But I think 3 by 5 is a what? Is a 15. And
3 is a...
3 by 5, because I could break this in 3 and 3 and then 5. 3 by 3 is going to be a 9 and a 5. Okay, I'm going to have to add. Let me just divide by the coefficient of the negative. This is going to be 3x squared minus 14x, and then plus 15 equals 0. Okay, and then I'd have my factor, in which case you have 3x and then x, and then I need 3 by 3, and then 5 will be here, because that's going to give me a 9, and I'm going to add. It's almost. So 3x is going to be equal to 5, or x is going to 3, x is going to 5 upon 3, or x again is going to 3. All right, I didn't have to repeat that. So I'm going to look for f of 3. You said you got a 0. Okay, I trust you there. F of 5 over 3. What did you get for f of 5 over 3?
I got negative 32 over 27.
Negative 32 over 27, which is equivalent to what?
That negative 1,1. Let's go 19.
Negative 1,19. So between negative 1 and
negative
negative
and negative. No, between. I mean, okay, it depends on the way you're looking at it, right? Sure.
All right.
I was gonna say, sure. No, but no, you know what? You're right. Between negative
between,
1 and negative 2.
okay.
Sure.
All right. So we use the second derivative test to find the maximum minimum turning point rather. Okay. So we know the output values. So this turning point is 3 and 0, and that turning point is 5 over 3 and negative 32 over 27. So we'll look for second derivative. This is also called the derivative of the derivative. So the squared y over the x squared, itaringana negative 6x plus 14. Remember, we're just basically testing. We're not looking for point of inflection. Or did they ask us to do that? No, they didn't say.
No, they didn't say.
So they're not looking for the points. They show all the stationary points and intercepts only. Okay. So we're negative 6 into, we're going to input 3. We're going to input at 3. What is the number that we'll get? Is it a positive or negative? Remember, we're not looking for a specific number. We just want to know if it's negative. But I think it's going to be negative. So here we're going to have a maximum.
It's 18 plus 14. Yeah, it's going to be negative. Sure.
All right. And then if we substitute a 5 over 3, we'll make this number way smaller. And if we subtract it from that 14, we're going to get a positive number. Here we have a minimum turning point. We've already talked about this part in terms of what happens. So this one is a maximum TP, and this one is going to be a minimum TP. Now with that, so we're looking for the intercept number 2. Intercept of the axis. So we started with the x-intercept, the y-intercept. So I'm just gonna do the y-intercept. We're gonna let x equals 0. All right.
I mean, but we also know that it's
the constant. So the y equals
the constant.
What is the constant here? Is a 9.
It's a 9. Yes.
Excuse me. It's going to be a 9. So we have the 9 here. So we intercepted 9 as 0 and 9. Excuse me. The x-intercept. So here is where the big deal is. We don't have the same case scenario as we did
the
last time. So give me the function. The function says f of x equals what?
Negative x cubed.
Negative x to the power 3.
Plus 7x squared.
Plus 7x squared.
Minus 15x.
Minus 15x
plus 9. Yeah.
So we could either use a synthetic or inspection. All right. To do it. So we could either use a synthetic or inspection. I particularly like inspection, but I like them both. But in both of them, we have to first find the factor theorem. Remember, factor theorem is basically using the remainder theorem, where specifically the remainder is 0.
Right.
So the remainder theorem are not different. Remainder is 0. So if I was in an exam, I would be very extremely smart, because I have where when I input f of some number 3, the output is 0. So if I was trying to catch up with the time, I will just use f3, which the output is going to be 0.
Sure.
Yeah, but usually we start from 1 and then build our way up. So let's try to find f of 1. Does the f of 1 give us 0 or not? All right. So the input 1 here, because that's how you do it. If length how come again factor. let's see if that's going to give us a 0.
Yeah. Put it in the calculator. X minus. Let's see, I plan ahead, bro. 1. 1. 1. Yeah. It is a
We get a 0.
factor.
Log 1 is a
Yeah,
factor.
we get it. So we get it. 1.
So I
Wait,
get
1 on
x minus
1 is right.
Okay.
Right.
X minus 1 is a factor. All right. So again, x to the power 3, 7x squared minus 15x plus a 9. So what I would like to do, since it's equated to 0, I would like to make this whole thing be divisible, but I would not really do that. I would just open one factor and the other factor and equate to 0. Here, I would put, I would just be specific. I'll put x minus 1 as a factor. So I'm looking for the number that I'm gonna multiply. Remember us doing this, right? X. I'm looking for the number that I'm gonna multiply by this, which is gonna give me that. What is that number?
The number that's gonna it's negative x squared.
Negative x squared. That was easy to come by. Okay, so we're gonna have a negative x squared.
Sure.
Negative x squared. Again, I'm looking for a number that I'm gonna multiply by this. This one. That's gonna give me a plus 9.
Wait, hold on. Let me follow.
By negative 1, get a positive 9.
Right. It's a negative 9.
A negative 9, good. Okay, so it's gonna be a negative.
Yeah.
So here I'm just gonna add plus bx. Right?
Bx. Yeah.
Okay. So what I'm gonna do
right.
is what I'm gonna do in this case is I'm gonna have to take this and this net multiplier and this also net multiplier. Is that difficult for you?
No. I'm looking at the notes we did, had right? On this.
Okay, very good. I like that. All right, so this is gonna give us bx squared. It's almost
right.
So do you remember when I said I helped you throughout? So that's going to give us a bx squared, and then this is going to give us a positive x squared. It's almost. And it's going to be a quadratic term in the function, which is obviously this. All right. Remember, we're looking for the quadratic term. That's
right.
It's almost.
Right.
So we take this constant, this quadratic x to the other side, it will minus. So it's going to be x squared. Sorry, I don't need a pencil, I want a pen. So bx squared equals 7x squared minus x squared. So bx squared equals 6x squared. And then we divide both sides by x squared. Now I divide by x squared. In which case x squared cancel x squared. That's a b. Nada. That's a 6. So b equals a positive 6. So I'm gonna go back there and put b as a positive 6. So over x minus 1, negative x squared plus 6x as a coefficient of that, and minus a 9.
Minus 9.
Those brackets equals 0.
0, right.
X minus 1. Factorize. But what I would like to do, I would like to get rid of the negative in front of the x. So I would then have to change it since this whole thing is going to equal to 0. Look, as x squared minus 6x plus 9. It can also work. All right. Let me equate this.
Right.
X is equals to 1. Here, I'm going to factorize into x and then x. Factors of 9 that are going to give 6 are 3 and 3.
It's 3 and 3.
No doubt about that. It's going to be
negative
minus equals to 0. X is 1 or X is
4 minus
or
3.
X is
Oh,
3.
3.
Right.
Right.
So again, we
Right.
talk about this term. This will come out twice. One representing a root, the other representing a turning point. Right.
Turning point. Right.
Again, this would be interpreted as f of 1 equals f of 3, also equals f of 3, which is equals to 0. That's our language. And we also know f prime of 3 is equals to a 0. So this someone can remind line because that's the language that they will sometimes use. All right, I think now we have everything together. We're ready to sketch. And as a homework,
right. Okay, sure. Thank you. I was about to mention that, like,
okay, as a homework,
is
sketch. I'm gonna send you more problem to sketch. But for now, as a
please
homework,
and thank you.
All right.
Like, thanks. No, thank you for having me.
All right, take care.
Good night. Oh, there we go. Right.